influenced by those defects, because defects are very small with respect to the size of this crystal. However, some of the properties like the color or the conductivity, those are very much influenced by this type of defect present in the ionic crystal, and that become very much important in terms of those optical or conductivity property which is coming due to the defect present in the crystal lattice is used in various. For example, the ionic solid having little defects is have semiconducting nature. The semiconducting activity is increased due to that, and that we can use in various electronic applications. So here is the wide range of work going on it to implement some defects within the suitable ionic solids to impose or to increase their semiconducting nature. Here we will discuss about the defect present in the some of the ionic crystal lattice. Okay. The types of defects may be stoichiometric defects and non-stoichiometric defects. Stoichiometric defects. Please keep your microphone switched off. Stoichiometric defects is actually the number of ions is not changing here. Only the position of ion is little different. And in case of non-stoichiometric defects, the composition is little different, like vacancies or empty position is present, or extra ion is present at interstitial position. Means either anion or cation is little excess. Extra ion is present in non-stoichiometric defects. But in stoichiometric defects, the composition is not changing. Composition is same as the perfect crystal, but it is having the defects. Okay, but in case of non-stoichiometric, anion, either anion or cation excess, or here is some deficiency. However, you have to keep in mind that here is no extra charges on the crystal. Crystal must be ionically neutral. No extra charge, negative or positive charge present, although excess ion is present. How it is possible in case of non-stoichiometric defects, that we'll discuss. First, regarding the stoichiometric defects, two defects is important. One is Frankel defect and other is Schottky defect. In case of Frankel defect, here one ion or atom is missing from its position and it is present in the interstitial, any of the interstitial position. Okay, if we show it in the figure, you can see that the actual position of this ion is where cross is present. This is the actual position of this ion, but this ion not present at that position, rather it is moved from here to this position. This is not the extra, it is only is coming from its original position to a new interstitial position at the crystal. So total number of cation and anion is exactly same. Okay, so one vacant space is created due to coming in new site, and at interstitial position an extra strain is developed or extra hindrance is developed. Okay, in case of ionic solid, this defect is common because the cation is having very smaller size with respect to the anions, very small size, and that is why the cation can easily accommodate in a interstitial position. And you have to also remember that this is not perfectly inelastic. Okay, so it is accommodated in a interstitial position from its original position. Generally, cation is coming at the interstitial position. Okay, so this is the Frankel defects. And Schottky defects is the defect when one anion and one cation. So pair of ions missing from the crystal lattice, but the position is as it is, but the anion and cation is absent. You can see here cation is absent and here anion is absent. So both the position is vacant, but neutrality is maintained because one anion and one cation is absent from the crystal. Composition is same, and the neutrality is also maintained, but the one anion and cation is missing, pair of ion is missing. That is the Schottky defects. Okay. Here in case of the other defects like non-stoichiometric defects, as we have mentioned that in non-stoichiometric defects, either metal will remain excess, metal means the cation, or the anion may be excess. So here is two types, three types, four types we are considering. One is metal excess defects due to anion vacancies, and metal excess defects due to interstitial cation. So metal excess may be created by two ways: if anion is missing or if cation is extra. Similarly, anion excess or metal deficiency may be created by two ways: metal deficiency by cation vacancy, if cation is missing, or having an extra anion occupied in interstitial site. Metal deficiency having extra anion. So metal excess due to anion vacancies, metal excess due to interstitial cation, metal deficiency due to cation vacancy, and metal deficiency due to extra anion occupied in interstitial site. Those are the four types of non-stoichiometric defects. And we'll discuss one by one. You have to keep in mind that, as I have already mentioned, the extra charge is not present on the crystal lattice, means neutrality is maintained. So to discuss the metal excess defects, here you can see this figure. This is the metal excess defect due to having the anion
interstitial cation.
metal excess defects due to anion vacancies. Anion is absent. If we see this crystal structure A plus B minus A plus B minus, this arrangement B minus A plus this arrangement, so here A plus B minus. B minus is missing, but to maintain the neutrality of the lattice, instead of anion, the electron is only present here. That is why although
अक्षय क्या हुआ बेटा? क्लास का क्या हुआ?
कुछ नहीं.
तुम फिर क्या?
अभी 10 बजे से.
अच्छा.
Please switch off your.
9:30 तो हो ही गया है. ठीक है?
Please switch off your microphone. Abhishek, who is Abhishek? Akshay, please switch off your microphone. Okay, so here you can see that the anion is missing and electron is occupying that hole, and that is why the electrical neutrality is maintained. That means the lattice is not bearing extra charge but having defects due to missing of negative ion. Okay, and that is anion vacancy in alkali metal halides. Heating alkali metal halide crystal. Alkali metal halide means, say, sodium chloride. Sodium chloride crystal is heated in atmosphere of alkali metal vapors. If we heat the sodium chloride in presence of sodium vapor, then the hole is created, because sodium vapor is reactive, so it takes one chlorine, and so it creates the vacant position in the crystal. This is known as F centers. F centers means the color bearing centers. This type of defect seen because of missing of anion from the regular hole, leaving a hole, regular site leaving a hole occupied by electron. And F center are possible for showing color by the compounds. Okay, F center means color center, and F center is created when the anion is missing from its position. Next, in case of metal excess defects due to cation at its interstitial position, like the Frankel defects, the cation is missing and occupied in a new position, but here extra cation is present. If extra cation is present, then the crystal must have extra charge, but that is maintained by the presence of electron at interstitial site. So one electron is also present at the interstitial site with that cation. Okay, and this is possible when, say, yellow color electrical conductivity non-stoichiometric ZNO, when there is no defect. ZNO is ZNO, the yellow color and electrical conductivity of this type of defect present, non-stoichiometric defect present, ZNO, is due to trapped electrons. Zinc oxide loses oxygen on heating, resulting number of cation become more than anion present in the zinc oxide. When we are heating, zinc oxide is loses oxygen, but electron present, and that is why the cation, extra cation present in interstitial position. Okay, such defects are called metal excess defects. Next is metal deficiency defects. Metal deficiency means cation is missing from its lattice. So here you can see the cation is missing and electrical neutrality is maintained. Nearest metal ion occupied 2 positive charge. When cation is missing means 1 positive charge is missing, but this positive charge is occupied by the nearby cation. So this cation is vacant and this cation is having 2 plus charge. Instead of 1 plus, it is giving 1 extra electron to maintain the neutrality, electrical neutrality of that crystal structure, of that lattice. Okay.
Yes, sir.
So here this type of defects in compounds where metal can exhibit variable valency means because extra charge when extra charge is possible on the metal, this type of defects is possible. Like nickel, it may accommodate extra charge, or Fe2 plus may accommodate extra charge to have Fe3 plus. So those transition compound which can accommodate an extra charge is possible to have metal deficiency defect by cation vacancy. Similarly, extra anion occupying the interstitial position. Extra anion present in the interstitial position and extra negative charge is balanced by 1 extra positive charge on the adjacent metal. Similar fashion, here 1 extra charge is present on the metal and 1 extra anion is present in the interstitial position. But this is the very rare case because it is very difficult to anion occupied in a interstitial site. This is because anion is larger in size. So it is not possible to accommodate within a small interstitial position. It is the theoretical importance, but here no example is known so far. Okay, there is no example because it is theoretically possible, we may consider. So I think now it is clear for you what is the defects present in the crystal. Here it is stoichiometric, non-stoichiometric. However, you have to keep in mind that electrical neutrality of the lattice is always maintained. No extra charge is present on the crystal lattice. Now, we have already mentioned that due to small defect present in the crystal lattice, the properties, especially optical and conductivity properties, is greatly influenced. Although density, strength, those is little influenced because the composition in case of stoichiometric defects, the composition is same, so those property is same. In non-stoichiometric defects, the change is very little with respect to a big crystal lattice. That is why those property is not changing. However, the semiconducting property or the optical property is very much influenced by this small defect present in the ionic crystal lattice. Okay. As we have already explained that transparent NaCl was colored yellowish when it was placed near a discharge tube. The coloration of NaCl and other crystal was responsible for the study of color center. Okay, a perfect NaCl crystal should not absorb any visible light. It is colorless. and transparent, but it becomes light yellow when we are heating. This is due to the defects present in the NaCl crystal, and which we are giving two names, F-centered and V-centered. F-centered is having original name German name, Farbe or Farbe. Farbe means color and Zentrum means center. So F center means color center. Okay. Here F center, as we have already mentioned, F center is due to the non-stoichiometric defects, metal excess due to anion vacancies. We have already mentioned it. Okay. So electron here, when we are heating the NaCl in sodium atmosphere, so sodium is giving the sodium plus and electron is leaving, and Na plus is incorporated at the NaCl and Cl vacancy is generated for excess of Na plus, and that Cl vacancy is occupied by the extra E minus. So here is the metal excess defect due to interstitial position of the cation. Okay, or it may also think, you may also think that Na plus is taking one Cl minus out, and instead of Cl minus, the E minus is occupied the position. Okay, so it is actually the metal excess by any of the means. Is it clear?
Yes, sir.
Yes, sir.
So we are having the color center, or we are having the light yellow color for the transparent NaCl. Similarly, if similar defects is present in NaCl, it may show pink color, KCl, it may show violet color. Okay, because absorption by this extra electron present. Next is V-centered. V-centered is possible to produce halide crystal containing excess halogen ions. So this is metal excess and this is halogen excess. Then we are calling it as a V-centered. If alkali halide crystal, alkali halide means sodium crystal, is heated in halogen vapor. If we are heating it in presence of halogen vapor, anion excess created. Excess halogen is introduced in its structure, and cation vacancy trap hole just as the anion vacancy trap electrons in F center. Cation vacancy is created, which is present as hole, positive charge. Okay. Thus, we should expect a whole new series of color centers produce excess metal. Okay. So, if possible, introduce excess halogen in KBr. The excess bromine center normal lattice position as negative ions and positive holes. Remember that in case of cation, here only the hole is present, electron deficit hole. Okay, so it is behave as a positive center, but cation is missing and electrical neutrality is maintained. This is known as V center. Is it clear?
Sir, could you please explain it once again?
Yes. In case of metal deficiency, you have seen that the metal ion is absent and extra charge is bearing the nearby metal ion. But in case of V-centered, it is also the anion halide excess. But halide's excess is not possible to have in interstitial position, as we have already mentioned, because halide or anion is bigger in size. So interstitial halide is not possible. How it possible? It possible to missing one cation, but only hole is present. Means positive charge like electron. If electron is present, then negative charge. Okay. Similarly, instead of the metal ion, here just hole is present. Means hole is behaving as a positive charge center. And that is why the halide excess is present. Is it clear?
Yes, sir. Understood.
Okay. So this is the V center. I think V center is not having the full name like the F center. It is only known as V center. Okay. So this is about the color centers, and we are getting the extra color due to having defects, and some material is used as optical material by introducing those defects. Okay. And here in modern electronics, the defect is very much important to have the improved semiconducting nature of crystal lattice. Like if we consider we have already know the classification of conductor, semiconductor and insulator. As we have mentioned, in case of metal, the valence band and the conduction band is overlapping due to metallic bond or electron C model, which we have discussed, or the valence band theory. We have discussed it in the band theory. So the electron can easily move from valence band to the conduction band in case of metal, and that is why those are good conductor, as this is very closely spaced or overlapping. But in case of semiconductor, distance is little higher. Here is little distance, and in case of insulator, the distance is very much high. So in case of semiconductor, we can overcome that distance to jump a electron from the valence shell to the conduction shell by giving some energy, means applying voltage or creating defects. If we create the defects, an extra band is generated inside this, so electron may jump using that band. Okay, like here, two types of categories of semiconductor is present. One is intrinsic semiconductor and one is extrinsic semiconductor. The classification is related to purity of the semiconductor. Intrinsic or pure semiconductor are those that are ideal with no defects, no external impurities. Means in intrinsic semiconductor, they weakly conduct electricity without having any defects in their crystal. And when we are imparting the defects or impurities, the conductivity is increased. But for external extrinsic semiconductor, we must have to introduce some defects within the crystal to get semiconducting nature. Okay, and this impurity present inside the crystal we are termed as doping. Doping means impurity present within the crystal lattice. Dopant. And doped means we are placing the impurity within the crystal lattice. Small extra impurity present, which is known as dopant. And doped means extra impurity present within that crystal. So it is doped state. There are two different ways adding a impurity. One is, I think you have the idea about the N-type dopant and P-type dopant. Okay, N-type materials like silicon or germanium atom in its pure form is doped with a element group 5. Okay, silicon or germanium, this is the silicon and it is doped by the group 5, antimony, arsenic or phosphorus. Here antimony we are giving. So you can also consider the octet rule. Say in case of silicon, outer shell is having 1, 2, 3, 4, 5 electron in their outer shell and 4 electrons of silicon. Silicon is having 4 electrons and Sb is having 5 electrons. So silicon is sharing 1 electron with the Sb. Now as 4 silicon is surrounded, so 1 extra 1, 2, 3, 4, 5, 6, 7, 8 and 1 extra electron is donated. And one extra electron is donated and this is present as the impurity within the lattice. This is known as N-type dopant. N means negative, means extra electron present as defect. Okay, but as hole is present on Sb, so electrical neutrality is maintained with extra electron. This is known as N-type material. Similarly, in case of the P-type material, silicon or germanium doped with the group 3 element. In group 3 element, here you can see around boron, there is 1, 2, 3 electron is present and from 4 silicon, it is sharing the 4. So total 4 plus 3, 7 electrons around the boron. But as per octet rule, it should have 8 electrons. So it is having the 1 vacant extra hole. So that extra hole is acting as defect for that crystal. And this is known as P-type. Hole is acting as a positive charge. That is why we are calling it as a P-type dopant or P-type material. P-type doping, P-type material, P-type dopant, N-type doping, this term is used. Okay, and doping is very much important to have the semiconducting nature for some of the extrinsic semiconductor. And for intrinsic semiconductor, we can improve the semiconductivity by imparting or by introducing the defects within the crystal structure. Is it clear?
Yes.
Yes, sir.
Okay. So that is all about the ionic solid metallic bond, and the defects present in the crystal lattice, especially in case of ionic solids. And defects is useful for the particular optical or semiconducting applications. We are not elaborating our discussion because time is very much short. So now we are moving to the next topic, that is coordinate bond or covalent coordinate bond. You can see that in the very first class we have classified the chemical bond into ionic bond, metallic bond, covalent bond and coordinate covalent bond. Ionic bond, covalent bond, metallic bond, coordinate covalent. Covalent bond actually we will discuss in the next chapter. For covalent bond is most common for the organic compound, so that we will discuss in the next chapter. And now we are discussing about the fourth type, that is coordination covalent bond. Coordinate covalent bond. So here actually in case of covalent bond, the covalent term is also present with that. So what is covalent bond? In case of covalent bond, the electron is equally shared by both the centers to have the attraction between them. In case of ionic bond, electron is transferred from one atom to other to have the charge on it, and in between them having electrostatic attraction. But in case of covalent bond, no electron transfer occurs, rather equally shared by both the centers to have the attraction between them, as if those are the common electrons present for both the centers. Okay. But when we are trying to draw the O2 molecule, we can draw by fulfilling the octet rule. But when we are trying to draw the O3 molecule, it is difficult by considering the octet rule. It is also difficult drawing using the Lewis dot structure. If you consider O2, it is easy to draw. Both is having octet fulfill if it is sharing the 2 electrons. Means total 4 electrons sharing by the 2 center. For O3, if we try to draw it, we must have to draw that 2 electrons from this oxygen is sharing by both the oxygen to fulfill the octet of both the oxygens. Sorry.